The Gauss law that we studied in electrostatics is analogous to the Ampere's law. Gauss law establishes a relation between the integral of the normal component of an electric field over a closed surface and the net charge enclosed by the closed surface, and helps in the calculation of the electric field intensity at a given point. Mathematically, it is represented as the integral over a closed surface S E dot ds is equal to Q by epsilon naught, where epsilon naught is the permittivity of free space. Ampere's law gives a relation between the integral of the tangential component of a magnetic field at points on a closed curve and the net current through the area bounded by the curve, and helps in the calculation of the magnetic induction at a given point. Ampere's law states that integral over a closed curve C B dot dl is equal to mu naught I, where mu naught is the magnetic permeability of free space. The Gauss law aims to calculate the electric field, whereas the Ampere's law aims to calculate the magnetic field. Let us discuss the Ampere's law in more detail. We shall discuss why we should consider only the tangential component of a magnetic field and neglect its normal component. We shall also discuss the sign convention for the currents to calculate the net current through an area enclosed by an Amperian loop. Let us consider a conducting wire carrying a current I. Consider a closed loop of any arbitrary shape around the conducting wire in a plane perpendicular to the plane of the conducting wire. Consider a small element of length dl on the boundary of the closed loop. B is the magnetic induction due to the current I passing through the conductor at the small element of the closed loop. The direction of the magnetic field at the small element can be found by using the right-hand thumb rule. On resolving the magnetic field into its two components, the component of the magnetic field along the length of the small element of the closed loop is called the tangential component of the magnetic field. Let it be Bt. And the component of the magnetic field perpendicular to the length of the small element of the closed loop is called the normal component of the magnetic field. Let it be Bn. The scalar product of the tangential component of the magnetic field and the length of the small element of the closed loop is Bt dot dl is equal to Bt dl cos theta. Since the angle theta between the tangential component of the magnetic field and the length of the small element of the closed loop is 0 degrees and cos 0 is equal to 1, Bt dot dl is equal to Bt dl. The scalar product of the normal component of the magnetic field and the length of the small element of the closed loop is Bn dot dl is equal to Bn dl cos theta. Since the angle theta between the normal component of the magnetic field and the length of the small element of the closed loop is 90 degrees and cos 90 is equal to 0, Bn dot dl is equal to 0. Hence, the normal component of the magnetic field can be ignored. According to Ampere's law, integral over the closed curve C Bt dot dl is equal to mu naught times the total current enclosed by the closed loop, I. That is, integral over the closed curve C Bt dl is equal to mu naught times I. This closed curve is called the Amperian loop. While using Ampere's law, sign conventions are also involved. Giving an arrow mark on the arbitrary shape of the curve assigns a sense to the curve. Now we shall discuss the rules to assign sign to the direction of a current in an Amperian loop. Let us consider multiple current-carrying conductors enclosed by an Amperian loop. Using the right-hand thumb rule, we can assign signs to these currents depending on the direction of their flow. Curl the fingers of the right hand along the arrow mark on the curve. Then, the currents along the direction of the stretched thumb are considered as positive, and the currents in the direction opposite to that of the stretched thumb are considered as negative. In this example, the currents I1, I3, and I5 are positive, and the currents I2 and I4 are negative. Let us now derive the expression for magnetic induction due to an infinite long straight current carrying conductor. Using Ampere's law. Consider an infinite long straight conductor carrying a current I. The magnetic field around the current carrying conductor is in the shape of circular loops. Consider an Amperian loop around the conductor in the shape of a circle. Let R be the radius of the Amperian loop. Consider a small element, dl, on the Amperian loop. The magnetic induction, B, at the small element of the Amperian loop, due to the current passing through the conductor, is tangential to the small element of the Amperian loop. We know that the scalar product of magnetic induction and the length of the small element of the Amperian loop, B dot dl, is equal to B dl cos theta. Since the magnetic field and the length of the small element of the Amperian loop are in the same direction, the angle between them is 0 degrees. Cos 0 is equal to 1. Therefore, B dot dl is equal to B dl. Let this be equation 1. According to Ampere's law, integral over the closed curve C, B dot dl is equal to mu naught I. On substituting equation 1 in the Ampere's law, we get integral over the closed curve C, B dl is equal to mu naught I. Let this be equation 2. Since the perpendicular distance r from the conductor to the periphery of the Amperian loop is constant, the magnetic induction B at every point on the boundary of the Amperian loop is constant. Then, equation 2 can be written as B into integral over the closed curve C, dl is equal to mu naught I. Let this be equation 3. The integral over the closed curve C, dl is equal to the total length of the Amperian loop, which is equal to the circumference of the circle. That is, integral over the closed curve C, dl is equal to 2 pi r. Let this be equation 4. Substituting equation 4 in equation 3, we get B into 2 pi r is equal to mu naught I. Then, B is equal to mu naught I by 2 pi r. Let this be equation 5. Thus, the magnetic induction at a distance r from the infinite straight current carrying conductor, B is equal to mu naught I by 2 pi r. Even if the conductor is infinitely long, the magnetic induction due to the conducting wire is finite. The magnetic induction is directly proportional to the current passing through the conducting wire. That is, B is directly proportional to I. The magnetic induction is also inversely proportional to the distance from the conducting wire. That is, B is inversely proportional to R. For a constant current, the magnetic field depends on R and possesses cylindrical symmetry. As the magnitude of the magnetic induction at every point on each concentric circular loop is constant. The direction of the magnetic field can be determined by using the right-hand thumb rule. Imagine a straight conducting wire held in your right hand. Stretch the thumb in the direction of the current. The curl of the fingers around the conductor represent the direction of the magnetic field. Let us now compare the Ampere's law and the Biot-Savart's law. The Ampere's law and the Biot-Savart's law help us to calculate the magnetic field due to the current passing through a conductor. The Biot-Savart's law is similar to Coulomb's law for electrostatics. According to the Coulomb's law, electric field strength at a point due to a charge is inversely proportional to the square of the distance from the charge to the point, that is, E is inversely proportional to R square. According to the Biot-Savart's law, the magnetic induction at a point due to the current-carrying conductor is inversely proportional to the square of the distance from the conductor to the point. That is, B is inversely proportional to R square. The Ampere's law is similar to the Gauss law for electrostatics. According to the Gauss law, integral over the closed surface S E dot ds is equal to Q by epsilon naught. According to the Ampere's law, integral over the closed curve C B dot dl is equal to mu naught I. Only when the symmetry of the situation allows us to take B outside the integral B dot dl, we can calculate the magnetic induction using the Ampere's law. It offers the most convenient way of calculating the magnetic induction, like in the case of a straight current-carrying conductor. Otherwise, we have to apply the Biot-Savart's law to calculate the magnetic induction, like in the case of a circular current-carrying conductor or of any shape. Now, let us discuss the application of Ampere's law to calculate the magnetic induction at a point inside and outside a straight current-carrying conductor. Let us consider a straight conductor of uniform circular cross-section with radius A, carrying a current I, which is uniformly distributed across the cross-section. Let us consider the direction of the current as coming out from the plane of the screen. Let us consider a point P outside the conducting wire at a distance R from the center of the cross-section of the wire. Consider an Amperian loop in the shape of a circle, concentric with the cross-section of the wire and having radius R, such that R is greater than A. The current enclosed by the Amperian loop is I, and the total length of the Amperian loop is equal to 2 pi R. That is, integral over the closed curve C dl is equal to 2 pi R. Let this be equation 6. From Ampere's circuital law, integral over the closed curve C B dot dl is equal to mu naught I. Let this be equation 7. Since the magnetic field at any point on the Amperian loop is in the direction of the tangent to the Amperian loop at that point, B dot dl can be written as BDL. Then, equation 7 can be written as integral over the closed curve C BDL is equal to mu naught I. Let this be equation 8. The magnetic induction at every point on the Amperian loop is constant. Then, B into integral over the closed curve C dl is equal to mu naught I. Let this be equation 9. Substituting equation 6 in equation 9, we arrive at the relation B into 2 pi R is equal to mu naught I. On rearranging the terms, we get the magnetic induction at the point P due to the current carrying wire B is equal to mu naught I by 2 pi r. Let this be equation 10. When the current passing through the conductor is constant, B is inversely proportional to R. Now, let us consider another case, in which the point P is inside the conductor at a distance r from the center of the cross-section of the wire. Consider an Amperian loop in the shape of a circle, concentric with the cross-section of the wire and having radius r such that r is less than a. Total length of the Amperian loop is equal to 2 pi r. That is, integral over the closed curve C dl is equal to 2 pi r. Let this be equation 11. The steady current passing through the conductor is I. Then the current distribution per unit area of cross-section of the conductor is equal to I by pi a square, where a is the radius of the conducting wire. Let this be equation 12. Then the total current enclosed by the Amperian loop, IE, is equal to I by pi a square into pi r square, where r is the radius of the Amperian loop. Let this be equation 13. From Ampere's law, integral over the closed curve C, B dot dl is equal to mu naught IE, where IE is the current enclosed by the Amperian loop. Let this be equation 14. Since the magnetic field at any point on the Amperian loop is in the direction of the tangent to the Amperian loop at that point, B dot dl can be written as B dl. Then, equation 14 can be written as integral over the closed curve C B dl is equal to mu naught IE. Let this be equation 15. The magnetic induction at every point on the Amperian loop is constant. Then, B into integral over the closed curve C dl is equal to mu naught IE. Let this be equation 16. Substituting equations 11 and 13 in equation 16, we get B into 2 pi r is equal to mu naught into I by pi a square into pi r square. On further simplification, we get B is equal to mu naught IR by pi a square. This equation shows that for all points where r is less than a, the magnetic induction B is directly proportional to r. If we plot a graph taking the distance from the current on x-axis and the magnetic field induction on y-axis, the graph is as shown. From the graph, it is clear that the magnetic induction varies linearly from the center of the cross-section of the wire to the periphery of the wire. And for all the points outside the conductor, the magnetic induction decreases with the increase in the distance from the center of the wire. A solenoid is a long wire wound in the shape of a helix. The solenoid is coated with insulated material such that the adjacent loops are insulated from each other. Let us now consider the given solenoid to have a length L and a radius of its circular loop R. Generally, the length of a solenoid is much greater than its radius. That is, L is much greater than R. Now let I be the current passing through the solenoid. This current-carrying solenoid produces a magnetic field. This can be easily understood by considering the field due to the individual circular loops. Let us now take a look at the cross-section view of the circular loops of the solenoid in the plane of the screen. Here, the dot mark with a concentric circle around it indicates the direction of current coming out from the plane of the screen, and the cross mark with a concentric circle around it indicates the direction of current going into the plane of the screen. Consider two adjacent circular loops placed coaxially and carrying equal currents. The magnetic fields at the midpoint between the peripheries of these two adjacent current-carrying circular loops are equal in magnitude but opposite in direction. Thus, the resultant magnetic field at the midpoint between the peripheries of the two adjacent coils is 0. The magnetic field inside the solenoid, either along the axis of the solenoid or along the radii closer to the axis, is uniform. To calculate the magnetic induction due to the current-carrying solenoid by using Ampere's law, consider an Amperian loop PQRS in the shape of a rectangle as shown. The PQ segment of the rectangular loop is along the axis of the solenoid and represents its length, denoted by h. Thus, the lengths PQ and RS are both equal to h. The segments QR and SP represent the breadth of the rectangular loop. According to Ampere's circuital law, integral over the closed loop B dot dl is equal to mu naught, i.e., the current enclosed by the Amperian loop. Let this be equation 1. This can be calculated by considering the magnetic fields along the lines PQ, QR, RS and SP of the Amperian loop. That is, integral over the closed loop B dot dl is equal to integral over PQ B dot dl plus integral over QR B dot dl plus integral over RS B dot dl plus integral over SP B dot dl, which is equal to mu naught IE. Let this be equation 2. The line segments QR and SP of the Amperian rectangular loop are perpendicular to the magnetic field. Thus, the angle between the direction of current through these segments of the loop and the direction of the magnetic field is 90 degrees. As cos 90 degrees is equal to 0, B dot dl is equal to B dl cos 90 degrees, which is equal to 0. Hence, integral over QR B dot dl is equal to integral over SP B dot dl is equal to 0. Let this be equation 3. The magnetic induction outside the solenoid is very less, and it becomes almost 0 as we move away from the solenoid. Hence, the magnetic induction outside the solenoid is assumed to be 0. Alternately, if we choose the Amperian rectangular loop such that its breadth is much greater than its length, the distance of the line segment RS becomes very far from the solenoid. Hence, the magnetic induction due to the solenoid at the segment RS is 0. Thus, integral over RS B dot dl is also equal to 0. Let this be equation 4. On substituting the equations 3 and 4 in the equation 2, we get integral over PQ B dot dl is equal to mu naught IE. Inside the solenoid, the line segment PQ of the loop is parallel to the magnetic field due to the solenoid. Thus, the angle between the line segment PQ and the magnetic field is 0 degrees and cos 0 degrees is equal to 1. Hence, the integral over PQ B dot dl is equal to integral over PQ B dl, which is equal to mu naught IE. Since the magnetic field inside the solenoid is uniform, which is a constant, we can write the equation as B into integral over PQ dl is equal to mu naught IE. As the length of the segment PQ is h, the equation can be written as B into h is equal to mu naught IE. Let this be equation 5. Let n be the total number of turns on the solenoid, and L be the length of the solenoid. Then, the number of turns per unit length n is equal to n by L. The number of turns included in the Amperian loop of length h is equal to number of turns per unit length into length of the Amperian loop. That is, NAL is equal to n into h. Let this be equation 6. The current through one turn of the solenoid is I. It is the same current through all the turns of the solenoid. Hence, the total current enclosed by the Amperian loop, IE, is equal to the number of turns of the solenoid bounded by the Amperian loop, NAL, into I. Let this be equation 7. On substituting equation 6 in equation 7, we get the total current enclosed by the Amperian loop, IE, is equal to NHI. Let this be equation 8. Substitute the value of IE from equation 8 in equation 5. We get B into H is equal to mu naught into NHI. This implies that the magnetic induction due to solenoid B is equal to mu naught Ni. Let this be equation 9. The direction of the magnetic field can be found using the right-hand thumb rule. From equation 9, it is clear that the magnitude of the magnetic field, B, is proportional to I. That is, the magnetic induction inside the solenoid is directly proportional to the current through the solenoid, when the number of loops of the solenoid is constant. Thus, as the magnitude of the current passing through the solenoid increases, the magnetic induction inside the solenoid also increases. B is proportional to N. That is, the magnetic induction is directly proportional to the number of turns per unit length of the solenoid, provided the current through the solenoid is constant. When the conducting wire is wound such that the turns are closely spaced, the number of turns per unit length increases. In this case, the strength of the magnetic field inside the solenoid also increases. The magnetic field inside the solenoid also depends on the nature of the material placed in the core of the solenoid. When a magnetic substance, like soft iron, is placed in the core of the solenoid, then the strength of the magnetic field inside the solenoid increases. This is due to the property of soft iron to allow a magnetic field to pass through it. Now let us discuss the application of Ampere's circuital law in the case of a toroid. A toroid is a hollow circular ring on which a large number of turns of an insulated conducting wire are closely wound. In other words, a toroid is a solenoid bent in a circular shape. Let I be the current passing through the toroid. For convenience, we ignore the ends of the wire of the toroid through which the current enters and leaves the coil, and consider the toroid wire as continuous without any endpoints. To calculate the magnetic induction due to the current-carrying toroid, let us consider 3 concentric circular Amperian loops, represented by 1, 2, and 3 around the toroid as shown, with their centers at the center of the toroid. The area enclosed by loop 1 lies in the interior open space of the toroid. Hence, it does not cut any turn of the toroid. The periphery of the area enclosed by loop 2 passes through the inside of the toroid such that each turn of the toroid is cut by the area of loop 2 once. On the other hand, the area bound by loop 3 extends over to the exterior space of the toroid. Hence, the area bound by loop 3 cuts each turn of the toroid twice. Let R1, R2, and R3 be the radii of the 3 Amperian circular loops respectively. Let B1, B2, and B3 be the magnetic inductions due to currents I1, I2, and I3 enclosed by the Amperian loops 1, 2, and 3 respectively. Consider the Amperian loop 1. According to Ampere's circuital law, integral over the closed loop 1 B1 dot dl is equal to mu naught I1. As the area bound by loop 1 does not cut any turn of the toroid, the net current enclosed by the Amperian loop 1 is I1 is equal to 0. Then, integral over the closed loop 1 B1 dot dl is equal to mu naught into 0. Hence, the magnetic induction due to the current enclosed by the Amperian loop 1 B1 is equal to 0. Now consider the Amperian loop 3. According to Ampere's law, integral over the closed loop 3 B3 dot dl is equal to mu naught I3. As the area bound by loop 3 cuts each turn of the toroid twice, each outer part of the turn in loop 3 has a corresponding inner part turn in the loop. Hence, the amount of current coming out from the plane of the screen is equal to the amount of current entering into the plane of the screen. Thus, the net current enclosed by loop 3 is equal to 0. Then, the integral over the closed loop 3 B3 dot dl is equal to mu naught into 0. Hence, the magnetic induction due to the current enclosed by the Amperian loop 3 B3 is equal to 0. Now consider the Amperian loop 2. According to Ampere's law, integral over the closed loop 2 B2 dot dl is equal to mu naught I2. For simplicity, let us assume that the radius of the Amperian loop 2 as R and magnetic induction B2 as B. Thus, the equation for the integral over the closed loop 2 is modified to B dot dl is equal to mu naught I2. In the core of the toroid, the length dl of the infinitesimal segment of the Amperian loop is in the direction of the magnetic field. Hence, the angle between them is 0. As cos 0 is 1, we get B dot dl equal to B dl cos 0, which is equal to B dl. Since the magnitude of the magnetic induction is constant inside the toroid, this equation can be represented as B integral over the closed loop 2 dl is equal to mu naught I2. The total length of the Amperian loop 2 is its circumference, which is equal to 2 pi r. Thus, B into 2 pi r is equal to mu naught I2. Let n be the total number of turns in the toroid. Therefore, the total current enclosed by the Amperian loop 2, I2, is equal to Ni. Substituting the value of I2 in the expression and simplifying, we get the magnetic induction due to the current carrying toroid B is equal to mu naught Ni by 2 pi r. Note that the magnetic induction is inversely proportional to the radius of the toroid, provided the other quantities in the expression are constant. That is, as the radius of the toroid increases, the magnetic induction decreases. Magnetic induction is directly proportional to the current passing through the toroid, when the other quantities in the expression are constant. Hence, as the current passing through the toroid increases, the magnetic induction increases. Magnetic induction is directly proportional to the number of turns of the toroid when the other quantities in the expression are constant. If we increase the number of turns per unit length of the toroid by winding the turns closer to each other, the magnetic induction due to the toroid also increases. Let us consider a straight current-carrying conductor, XY, of infinite length. And like any current-carrying conductor, it produces a magnetic field around it. Now we introduce another straight current-carrying conductor, PQ, of infinite length above XY. This new conductor is in the external magnetic field of the conductor XY such that PQ is parallel to XY. Now, we will notice that due to the external magnetic field of the conductor XY, the conductor PQ experiences a magnetic force. This implies that there will also be a force on XY due to PQ in accordance with Newton's third law. From this, we can understand that two straight parallel current-carrying conductors placed close to each other exert force on each other, because they lie in the magnetic fields produced by one another. Now let us find the force of attraction between the conductors carrying currents in the same direction. Let us first find the force exerted by conductor XY on conductor PQ. Let the currents passing through the two straight conductors XY and PQ be I1 and I2 respectively. Let the current through both the conductors be in the same direction. Let D be the distance between them. The magnitude of the magnetic field induction is constant at all the points, which are at equal distances from the conductor. Let the magnitude of magnetic induction due to current in XY at PQ be B1. The direction of the magnetic induction B1 at PQ can be found by using the right-hand rule. If we place a stretched right hand such that the thumb indicates the direction of current in XY, the direction of curl of the four fingers of the hand indicates the direction of the magnetic field due to the current in XY as shown. The magnitude of magnetic induction at any point along conductor PQ due to current in conductor XY is B1 is equal to mu naught I1 by 2 pi d. Let this be equation 1. The magnitude of the force experienced by a segment of length L of the conductor PQ due to the magnetic field produced by the conductor XY is F21 is equal to B1 I2 L sin theta, where theta is the angle between the direction of the magnetic field B1 and the current in the conductor PQ. Let this be equation 2. Here, theta is equal to 90 degrees and sin 90 is equal to 1. Therefore, the force acting on the segment of the conductor PQ of length L due to the conductor XY is equal to F21 is equal to B1 I2L. Let this be equation 3. On substituting the value of B1 from equation 1 in equation 3, we arrive at the expression F21 is equal to mu naught I1 I2 by 2 pi d into L. Let this be equation 4. The direction of the force experienced by conductor PQ due to the magnetic field produced by the conductor XY can be found using Fleming's left-hand rule. According to Fleming's left-hand rule, stretch the 3 fingers, thumb, forefinger, and central finger of your left hand mutually perpendicular to each other. If the central finger represents the direction of the current and the forefinger represents the direction of the magnetic field, then the direction of the thumb represents the direction of the force acting on the current-carrying conductor. Thus, the force F21 is directed towards the conductor XY. As discussed earlier, the current-carrying conductor XY experiences the same force due to the magnetic field produced by the current I2 in the conductor PQ. This is in line with Newton's third law. The magnitude of the magnetic induction due to the current-carrying conductor PQ is B2 is equal to mu naught I2 by 2 pi d. Let this be equation 5. The direction of the magnetic induction due to current I2 through PQ can be found by the right-hand rule. The magnitude of the force acting on the segment conductor XY of length L due to the magnetic field produced by the current through conductor PQ is F12 is equal to B2I1L, which is equal to mu naught I1 I2 by 2 pi d into L. Let this be equation 6. The direction of this force can be found by using Fleming's left-hand rule, and the force acting on the conductor XY is towards the conductor PQ. When you compare equations 4 and 6, you realize the two forces, F21 and F12, are equal in magnitude but act in opposite directions towards each other. Hence, if the currents in the two parallel straight current-carrying conductors are in the same direction, the two conductors attract each other. On the other hand, if the currents in the two straight parallel conducting wires are in opposite directions, then the forces exerted by the conductors on each other are equal in magnitude but repulsive in nature. Thus, they repel each other. Thus, the magnitude of the force F between two parallel conductors of infinite length L, separated by distance d, carrying current I1 and I2 respectively in them, is equal to mu naught I1 I2 by 2 pi d into L. Let this be equation 7. Therefore, the force acting per unit length of the conductor F is equal to F by L, which is equal to mu naught I1 I2 by 2 pi d. Let this be equation 8. Using this expression for force per unit length, let us now define the SI unit, ampere. Let the distance of separation between the conductors D be equal to 1 unit, which is 1 meter. Let the current through the two conductors be equal to 1 unit, which is 1 ampere. Then, the force per unit length becomes mu naught by 2 pi. On substituting the value of mu naught, which is 4 pi into 10 power minus 7, we get F equal to 2 into 10 power minus 7 Newton per meter. Thus, if two straight parallel conductors of infinite length, separated by a distance of 1 meter in vacuum, exert a force of 2 into 10 power minus 7 Newton per meter on each other, then the current passing through each conductor is said to be 1 ampere. The SI unit of charge is also defined from the unit of current. If a constant current of 1 ampere passes through the cross-section of a conductor in 1 second, then the charge passing through it is said to be 1 coulomb. Practically, it is not possible to demonstrate the force between the two current-carrying conductors we discussed, as the effects of magnetism are generally smaller than the effects of electricity. To study a similar effect of force, as between two current-carrying conductors, we replace the straight long wires with a coil of suitable dimensions and number of turns. We refer to this as Roget's spiral. Consider a soft spring with a natural frequency of oscillation equal to 1 Hz or with a natural time period of oscillation as 1 second, suspended vertically from a rigid support. Take some mercury in a bowl and place it exactly below the suspended spring in such a way that the lower end of the spring is just in contact with the surface of the mercury. Take a DC current source, connect one of the terminals to the top of the spring, and the other terminal is connected to a switch. And then it is dipped in the mercury taken in the bowl, so that the circuit gets closed. When the circuit is switched on, due to a constant current passing through the adjacent turns of the spring, the coils attract each other, and the spring comes out from the mercury and the circuit is broken. As a natural action, the spring relaxes and again comes in contact with the surface of the mercury. Then the circuit gets closed and again the adjacent loops attract due to the current in the coil. The force of attraction between two adjacent loops in the coil is similar to the force of attraction between two parallel current-carrying conductors, when the direction of current through them is the same. While doing this activity, we should take care to keep the face away from the mercury vapors, because mercury vapors are poisonous.